Hey there, PAP students. Welcome to today's discussion answers video on chemical rates and energy. I'm going to walk you through the questions, draw out a few examples, and show you some different things that will hopefully help you with your understanding of the questions for today's discussion. So let's jump into things here. Number one said list 2 to 3 examples of the different forms or types of energy that can be released by a chemical reaction. So there are several different types. I told you to list at least 2 or 3 of them, but you should have listed things like heat energy, sound energy, light energy, electricity. Those are all different forms, or if you said thermal energy, that would be fine. Those are all different types of energy that we could potentially see released by a chemical reaction. Okay. Number 2, describe why the formation and breaking of bonds are important when describing energy input and output during a chemical reaction. So I recorded a video earlier to kind of show you some examples of this, so I'm going to go ahead and play that right now.
All right, so for number 2 here, we're talking about the breaking and forming of bonds and the relationship between that and the energy input and output of a reaction. So first we need to understand, what happens in terms of energy when bonds are being broken, and then what happens in terms of energy when new bonds are formed. So the first thing you need to understand is that in every chemical reaction, there's the breaking of bonds and the forming of new bonds. Typically, the breaking of bonds happens on the reactant side of the reaction. The forming of new bonds happens on the product side of the reaction. Okay, so in every reaction, you have bonds that are being broken on the reactant side and new bonds that are being formed on the product side, and that's why we get new compounds or new things on the product side of a reaction. Okay, so the breaking of bonds requires energy. In order to break a bond, we have to input energy, or the reaction has to absorb energy, and that's typically what we call the activation energy. Okay, forming of new bonds actually releases energy. Okay, so that energy that gets released is a result of the formation of new bonds. Okay, so in every reaction we have breaking and forming, which means we have energy that's required as well as energy that's released. Okay, the required energy is going to be on the reactant side. That's called the activation energy. Oftentimes that's the energy that's needed to get the reaction started. The forming of new bonds happens on the product side, and that is where energy is often released. Okay, now we're going to get to, in just a second, we'll talk more about the relationship between activation and released energy, because that's what's going to determine exergonic versus endergonic. And we'll get into that here in just a second with the next question.
All right, so looking at the next question, number 3 here said define the term exergonic in terms of energy input and output. What is happening during the reaction that makes it exergonic? So this, again, I recorded earlier to kind of show you visually what this is looking at. So we're going to go ahead and move on to the next question here.
All right, so the first part of number 3 here was to define the term exergonic. So when we're talking about exergonic, essentially this is a reaction that releases excess energy. Okay, meaning that there's going to be extra energy that's released on the product side of the reaction. Okay, now in order for a reaction to be exergonic, what this means is that the released energy on the product side, remember the released energy comes from the forming of new bonds, okay, is going to be greater than the activation energy. And remember that the activation energy was the energy needed to break the bonds of the initial compounds on the reactant side. Okay, so in an exergonic reaction, the released energy on the product side is always going to be greater than the activation energy on the reactant side. Okay, another way to look at this is that the output energy is going to be greater than the input energy. Okay, so that's another way to look at it in terms of input and output. Right? So essentially what this means is that in a reaction that's exergonic, the amount of energy that's needed to break the original bonds is not as much as the amount of energy that's released when the new bonds form. And so essentially we get this excess energy on the product side because of the amount of energy that was released as a result of forming new bonds.
All right, so we'll go back to number 4 here. Number 4 said compare and contrast the terms exergonic and exothermic. So the first thing you should notice with these two terms is that they both start with the same, what we would call a prefix, which is that ex or exo prefix, which basically is similar to the word exit, okay, which means to release or to go out. So both of these terms refer to reactions that release energy, or there's energy coming out of them. However, the only difference really between them is that exergonic is a more generic term. It refers to just any reaction that releases any kind of energy, whereas exothermic is a more specific term because it refers specifically to thermal energy or heat energy. Okay, so exothermic is a term that you can only use to describe a reaction that releases heat energy, whereas exergonic can be used to describe any reaction that releases any type of energy. It could be heat energy, it could be light energy, it could be sound energy, it could be any of them. So exergonic is a more generic term. Exothermic is a more specific term related to heat. Okay. Number 5 said define the term endergonic. What are some ways in which we can give energy to a reaction? So I'm going to go back to my videos that I recorded earlier to show you some examples of this.
All right, for number 5 here, we're talking about endergonic reactions. So first of all, to kind of define what endergonic is. So we defined before that exergonic is the release of excess energy. Endergonic is actually the absorption of energy. Okay, so it's a reaction, it's a chemical reaction that absorbs more energy than it releases. So we can look at this with the greater than symbols here. We can say that the energy that's required to activate the reaction, the activation energy, is greater than the released energy. Meaning that the amount of energy it takes to break the original bonds on the reactant side is going to be greater than the amount of energy that's released as a result of the new bonds forming. Okay? Another way we can look at this is to say that the input energy, the energy that is put into the reaction, is greater than the energy that comes out of the reaction. Okay, so that's how you would define an endergonic reaction. The second part of this question was dealing with what are some ways in which we can give energy to a reaction. We can do things like add light, we can add heat, we can add sound energy potentially, we can add electricity. Okay, these are all forms of energy that we can add to a reaction and give it as a form of activation energy to get it started. And so those are all the different ways, or some of the different ways that we can add energy to a reaction.
All right, so let's take a look at number 6 here. Number 6 said compare and contrast the terms endergonic and endothermic. So this is obviously very similar to number 4. Again, endergonic is just a more generic term that refers to any reaction that absorbs any kind of energy, whereas endothermic is referring to the absorption of heat energy specifically. So again, it's the same kind of deal, except this time we're looking at the prefix endo, which means to absorb rather than release. Okay. Number 7 said give at least 1 to 2 examples of some exothermic reactions and some endothermic reactions. I'm going to give you just one example for each here. There's a couple great examples in the form of heat packs and cold packs. If you're familiar with, a heat pack or like one of those ice packs where you have to kind of punch it to get it to start getting cool or getting warm, those are actually chemical reactions. And when you punch it to get it to start, what you're doing is you're breaking a capsule inside that causes chemicals to mix and causes a chemical reaction to start. So the heat pack would obviously be a exothermic reaction because it's releasing heat. That's why you feel it as being hot, is because it's releasing excess energy in the form of heat. Okay, the cold pack would be an example of an endothermic reaction because that's actually absorbing or kind of removing heat from the surrounding area. So when something removes heat, that means it's cold, right? So the removal of heat versus the releasing of heat, that's the difference between the two. So a cold pack and a hot pack would be great examples of endo and exothermic reactions. The cold pack being endothermic, the heat pack being an exothermic. Okay, this would also apply to like hand warmers if you've used those in the winter, those kind of things. Again, that's an exothermic reaction because it's releasing heat. Okay, last one, number 8 here. Overall, is energy conserved in chemical reactions and explained? So the answer to this question is yes. Energy is always conserved, meaning that the amount of energy that is in the bonds originally on the reactant side is going to be somewhere on the product side. Okay, it might not be within the bonds. It might be just excess energy in the form of light or heat or sound or those kind of things. But if you take the total amount of energy that's on the reactant side, whether it's in a bond or whether it's not in a bond, and you compare that to the total amount of energy that's on the product side, it's going to be the same. Okay, regardless of where that energy is, all that energy is still there in some form, whether it's separated from the bonds or whether it's contained within the bonds. That energy is still there. It's just like law of conservation of mass that we've talked about with balancing equations. Same thing applies here. Is the reactant mass is equal to the product mass. Well, in this case, the reactant energy is equal to the product energy. So yes, energy is in fact conserved throughout a chemical reaction. So that wraps up our discussion for today. Let me know if you have questions. Thanks.